All right, guys, I'm going to try and make this short just to give you a general idea of the first day lesson, but there's a lot to go over. So the ideas we're looking at today is what is the function approaching. So if we look at this problem, this one right here, we have a graph of f. We start by saying what is f of -1? Well, that is wherever the hole is filled in. So hole is filled in right here. So that's equal to 3. As you approach x equals -1 from the left side, what is f of x approaching? So approaching x from the left side, that's approaching +1. Same thing from the right side. Follow it from the right side. It's approaching -1. What about x equals 1? So same 3 questions for x equals 1. If you look at x equals 1, if I can get it selected, there we go. If we look at x equals 1, there's no point where it's filled in, so it does not exist, or let's put it this way, f of 1 does not exist. If you look at it from the left, it equals -2. If you look at it from the right, it equals -2. Left, right. Okay, so the point does not exist, but we can approach it from the left and the right. What about this one? Same kind of general idea. As we approach x equals 1 from the left, what is the graph of g approaching? All right, so approach from the left. It looks like it's approaching -2. As we approach from the right, what does it look like we're approaching? Looks like we're approaching -1. This time we do have a filled-in point, though. Notice how the point itself doesn't actually change what we're saying we're approaching. When we're talking about approaching, we are just following the curve of the graph and saying, what is it getting closer to? Okay? Keep that in mind as we go through this. I also want you to graph this one. You can use a calculator and graph this one. Do the same thing at x equals 1. Now, when you pull up your graph, you're going to get something like this. But when we look at x equals 1, there should be something missing here. All right, if we think back to pre-calculus, if we plug in 1, we get 0 over 0. That cancels out. That should have ended up giving us, or 0 over 0 doesn't cancel out, but that means something should cancel out. And so we should have ended up with a hole there. Our graph just won't show us the hole. So let's think about what it approaches. So if we approach from the left, we're approaching 3. If we approach from the right, we're approaching 3. And so it looks like we're approaching 3 there. This idea of looking at what we're approaching is the idea behind limits. The limit as x approaches some constant of f of x is equal to L. This is the idea behind limits. So what we found here, we found the limit as x approaches 1 from the left of y, or you could write out the whole function, equals 3. And the limit as x approaches 1 from the right of y is equal to 3. Okay, so let's start with some problems that you can try. Try this one by graphing. So look at your graph in the calculator. All right, and then you could pause the video and do it so you don't see the answer. So you should have gotten the graph, should have ended up being just a straight line here between 0, -1, or yeah, 0, -1 and 1, 0. Which means if we're looking at the limit as x equals 2, should have had a hole there, and that should end up equaling 1. We can do this tabularly as well, so looking at a table. So let's say you had this set up and you were looking at this table. As you approach -1, what does it look like? All right, so let's talk. If we approach -1, -1's error, but on this side, it looks like we're getting closer to -5. And on this side, it also looks like we're getting closer to -5. So we'll say this limit is -5. Now, one of the key features here, why I'm not writing out limit from the left, limit from the right, is that if the limit from the left and the right approach the same thing, that's just what the limit is. So this is equal to 1. This is equal to -5, because the limit from the left and the right are the same. All right. This is a worksheet we did in class. I'm not going to make you do it right now. You can do it if you want and ask me for the answers. But this is just getting you to write out limits. So for example, This one right here for b, this would be the limit as x approaches 0 from the left of g of x is equal to 2. That's what we're asking you to do in those boxes. So feel free to work on those. This statement down here is how you would say this. So the limit of g of x, or the limit as x approaches a number of g of x, is equal to blank. All right? This is how I want you saying it in class when we actually start working on this more. All right, last one we're going to look at that does work. Now, we said a minute ago that if the limit from the left and the limit from the right meet at the same place, then that's what the limit is. So we're looking at the limit as x approaches 1 here, which means we need the limit from the left and the right of that. So limit as x approaches 1 from the left. Oops. There you go. And the limit as x approaches 1 from the right. So I want you to try and figure it out yourself. Pause the video, see if you can figure it out, whether by graphing or if you have another way you think you can do it. All right, welcome back. Let's look. So we're looking at the left here on this side, looking at the left, and we have a piecewise function. So this one says x is less than 1. This one says x is greater than or equal to 1. Which one of those represents the left? Well, this one represents the left. Less than 1 is to the left of 1. So really this limit is looking at as x approaches 1 from the left of x minus 2. And that should be easy enough to graph. I mean, honestly, you could probably look at that and figure out what this limit is. This should equal -1. Then on this side, same thing. This one's now the right, so limit as x approaches 1 from the right of -square root of x. Once again, you should be able to graph that, figure out what we're looking at. As we approach 1 from the right, that gives us -1. So limit from the left equals limit from the right, and that equals -1. Oops, lost my answer. All right, let's look at another similar case where this doesn't work like we wanted. So I want you to go ahead and graph this in your calculator. All right, welcome back. So we should have something like this, or what you should see on the calculator. Now, what your calculator doesn't show you is that there should be a hole there. And so let's look at it again. Limit as x approaches 0 of f of x. We're looking from the left and the right. So if we look at the limit as x approaches 0 from the left, you should be able to see it goes to -1. And then as we approach 0 from the right, that should be 0, it's +1. This time, these don't equal to each other. So this is our first case of a limit not actually being able to be found. We call this that the limit does not exist. We have 3 cases that will make it does not exist. The first is like this, where the left does not equal the right. Left does not equal the right. All right, let's look at the next case. Go ahead and graph this one, and I want you to try and figure out the limit as x approaches 0 of f of x. Okay, welcome back. So graphing it, you should have seen something like this. There we go. All right, so once again, from the left, limit as x approaches 0 of f of x. From the left, we end up going to positive infinity. And limit as x approaches 0 from the right of f of x goes to positive infinity as well. And so you're probably looking at yourself like, yeah, Mr. Idell, I got this. It's not an issue. But you're going to notice some problems here. Because while this is infinity, it technically also does not exist. This is what we call unbound behavior. Anytime a limit goes to infinity, it does not exist. It's considered unbound behavior. Now, there's a caveat here. This is the only form of does not exist where we can give you a quote-unquote value as well, because infinity, you can argue it's not actually a value. But this is the only case where we can give you a value as well. So positive infinity is an answer here. does not exist is also an answer here. Now, if these went to different infinities, it would just be does not exist because they don't go to the same thing. So keep that in mind. This is the last case. Now, I want you to do two things at once here. We'll call this one g of x. I want you to look at both of these. So this one, I want you to look at the limit as x approaches 0. This one, I want you to look at the limit as x goes to infinity. I want you to find them both using your calculator. This one over here should be pretty easy. Right? The sine of x should be easy. Sine of 1 over x is going to be a little bit tougher. Well, I say sine of x should be easy. It should be easy to graph and visually see. Sine of 1 over x is going to be a little bit tougher. Okay? What you'll need to do for sine of 1 of x is zoom in. Oops. And you're going to have to do that multiple times. All right, go. All right, so you're back. Let's start with this one, which is the one most of y'all would have started with. If you zoomed in a few times, you probably would have gotten frustrated and been like, Mr. Idle, I can't tell, I'm done with this. Because you saw something like this going on. This is me frantically scribbling it down. You saw something like that going on, bouncing rapidly back and forth. Right? This is going to end up being does not exist. Right? It does not exist for a reason we call oscillation. It means as you get closer and closer to your value you want to approach, the function is rapidly bouncing between two values. And your graph can't even accurately show this. This is so fast that there shouldn't really even be a line drawn to connect them. It goes straight from the highest value to the lowest value as quickly as it possibly can. Okay? So that does not exist. Now the reason we put this other one up here as well is because it's another way to see it and to get a visual understanding. So let's think about sine of x. This is the graph of sine of x. As we go to infinity, is this ever going to approach a single number? You should be thinking about the graph of sine and be like, no, it goes on forever. Okay, so it goes on forever. And what is it doing as it goes on forever? Well, it's constantly bouncing between a high point up here and a low point. And it'll do that forever and ever. This is also oscillation. It is bouncing between a high point and low point. It just happens much slower than the oscillation at 0 for the sine of 1 over x. So both of these do not exist, and it's because of oscillation. All right, so reasons for unbound behavior. Reason for does not exist. Unbound behavior, infinity or negative infinity. Behavior differs from the left and the right, so they do not equal. And then oscillation, so it bounces back and forth forever and ever and ever. Okay? All right, that's it for today. Y'all have a great day.